Welcome to the examples videos for the trigonometric identities module of the Extension 1 bridging courses. In this video, I will go through a simple example of combining a sine and a cos function into a single sine function. We'll then progress to do a more complex example, and in the last video, we will work through the theory behind combining sine and cos functions into a single sine function. So in this example, what we're going to do is to combine or write a half sine of t plus root 3 on 2 cos of t as just one single function. So here what we want to do is write this thing as a single a sine of a function plus some sort of horizontal shift. So what we want to do in combining these is that we need to firstly find the amplitude A. So we're interested in combining these two, and we want to find out what's the amplitude of the new combined function. So to do this, we use that A is equal to the square root of the thing in front of the sine function squared plus the thing in front of the cos function squared. This thing here is our A, and this thing here is our A. This thing here is our b, the thing in front of the cos function. This thing here is our b. So to find the amplitude of our new combined function, this is going to be a half squared plus root 3 on 2 squared. And this is the square root of 1 on 4 plus 3 on 4, which turns out to be the square root of 4 on 4, which is in this case simply 1. So when we combine these two, the amplitude, or the half of the peak to peak distance, is going to be 1. We found that. So step 2 is to find the quadrant for alpha. So to do this, we know that cos of alpha is the thing in front of the sine divided by the amplitude, and we know that sine of alpha is the thing in front of the cos, our b, divided by the amplitude. So that means that sine of alpha, the thing in front of the cos, is root 3 on 2, root 3 on 2. The amplitude we've found is 1. Sorry, that should be cos. Cos alpha is the thing in front of the sine, and sine alpha is the thing in front of the cos, which is... that was wrong, sorry. Actually, I might start from... if I can, I'll start from here. Okay, so to find alpha, we know that sine of alpha is the thing in front of the cos, that's root 3 on 2, divided by the amplitude, which is 1. And cos of alpha is the thing in front of the sine, which is a half, divided by the amplitude, which is 1. So in this case here, we've got that sine of alpha is root 3 on 2, cos of alpha is a half, and we note that both of these are positive. So we use the sign, the SIGN of sine and cos, to decide what quadrant alpha is going to be in. In this case, both sine and cos are positive, and we know that all are positive in the first quadrant, so alpha is somewhere here. So to find alpha from here, we know that we're in the first quadrant. We also know that cos of alpha is root 3 on 2. Sine of alpha is 1 divided by 2. By using half of an equilateral triangle and Pythagoras theorem, we know that this must be 60 degrees or pi on 3. Sine of this is root 3 on 2. Cos of this is 1 on 2, so therefore alpha has to equal pi on 3. So this is step 4. Step 3 is to find alpha. And the final step, step 4, is to write what the final answer is. So I'll do this up here. Step 4. Write the final answer. So our amplitude we found was 1. And we found that our alpha was equal to pi on 3. So we've combined a half sine t, root 3 on 2 cos t, as a single function of 1 times sine of t plus pi on 3. The important thing to note about this is that this is very much easier to plot than these two graphs, and that's why we're trying to do this. So for example, if I wanted to plot the two graphs separately, I'd have to try and plot sine. I'd have to work out what a half sine looks like. That would be a half, this would be minus a half. I'd have to plot cos, which looks like a separate function, and I'd have to, the amplitude of this is root 3 on 2, so it would be cos, it would be a bit bigger. It'd go down further and up. You can see that it's messy. And then I'd have to add these two together to give a point, add these two together to give another point, etc., and then join up all the dots. This is much easier to plot. Here, we know the amplitude is 1 and the horizontal shift is pi on 3. So this, if we were to plot sine, for example, we know that the normal sine graph looks like this. This is 2 pi, this is pi. To plot this is much easier. The plus pi on 3 moves the graph to the left by pi on 3, and so the graph of this combined function is simply the sine graph moved to the left by pi on 3. So this will be minus pi on 3, this will be pi minus pi on 3, etc. This is y is equal to sine of t. This is y is equal to sine of t plus pi on 3. And that is much simpler to plot than trying to plot these two graphs together. So to summarise, what we've done is we've used the coefficients of the sine and the cos to find the amplitude. We've combined these two coefficients to find sine and cos of the horizontal shift. We've then found alpha, and then we can write our two functions as a single function. And just to recap, one of the reasons why we might do this is that it's a whole lot easier to sketch that than to sketch those two, and it's a whole lot easier to solve equations for those as well. We'll see you for the next example.